So before we go on to the charge balance, we're going to do a little bit of a sampler platter of the site fillings. And the reason we're going to do this is because one of the components here, the sum of the negative charge, actually requires that we know what the amount of OH versus oxygen is in the OH site. And so we at the very least have to do that site filling first. Although we'll also do the tetrahedral site so that you get a little bit of an idea of what this is going to look like. Before we get there, I was a little frustrated before that the formatting didn't copy over, and so I'm going to actually paste the formatting over here. Let me see if I can get this correct. So we will, nope, format, that's what I want the formats, and so now we have they look a little prettier. And again, we talked earlier about sort of the importance of sort of good accounting, good bookkeeping to kind of keep this thing in such a way that you can recognize sort of what you're doing. Okay, so we have these normalization factors, and this is going to be the critical number that we're going to use to calculate all of our site fillings. So let's skip ahead here, and we are going to look at the very first set of site fillings. And normally the way that we want to do this is we typically start with the smallest cation site first, and then we build our way towards the larger cation sites. And the reason we do this is because essentially we're going to put the small things in first, and then whatever empty space we have left over, we're going to begin to put slightly larger things in there. And if there isn't enough room, those things are then going to get pushed into the next larger site. And you can see that, for example, here, that we have silicon in the tetrahedral site, we have aluminum in the tetrahedral site, but then again we have aluminum in the 6-coordinated site as well. So clearly we're going to have to come up with some formulas that allow us to put some aluminum in here, but potentially put some aluminum in here as well. So let's start off with silicon, because in amphiboles there's only one site that we are allowed to put the silicon in. That's the tetrahedral site. So the way that this formula works, it will be the equal sign. We need the normalization factor. Find that here. So there we go. And I like putting the dollar sign in front of here, in front of the column. In that case, if I am copying this column further to the right, that the normalization factor will be retained. Now it's not absolutely necessary that you do that, but if you don't do that, then you've got to be kind of extra careful when you're copying cells to kind of pay attention and make sure that that you're always referring back to the normalization factor column. So this is sort of a little bit of insurance to kind of help make sure that I do that. So there we have the normalization factor, and then I am going to multiply that by the raw silicon moles. There we go, and I hit return, and we see that we have 7 moles of silicon. And the funny thing is, if you go back and look at the original amphibole formula, my kind of hypothetical amphibole, you'll see that I indeed started with 7 moles of silicon. Again, the reason why that is exactly 7 and not something like 7.3 or 6.8 or something like that is because, again, I picked the weight percents in order to work out to these perfect integer values, at least for these first test cases down here. Now again, when we get to our mystery amphibole, it's going to get a little bit more exciting. We'll actually see a little bit more of a realistic scenario of what it's going to look like. But for these kind of initial test cases, I just want to make sure that the formulas work. I also want to give you, the viewer, the opportunity to see how these are put together, and if the numbers are kind of sort of easy to recognize, I think that makes it a little easier for viewers to see. Okay, so we have a silicon number here, and so now we need to figure out what the aluminum number is going to be. Now, you might think that, oh, well, we just want to do the same thing, and so we're going to just go, this is going to be equal to the normalization factor, put our dollar sign there in front of it, and then we will just simply multiply it by aluminum, and everything will be all fine and dandy, okay? So we do that, and we see, we have a problem because we are only allowed to have a total of 8 cations in the site, and you see that we actually have 9 cations in the site. And in fact, when you look back at the original formula for catiphorite, you can see that aluminum actually is distributed between 2 different sites. And so this is a completely wrong calculation here. And so we want to get rid of this, and we want to think about what is the correct way to do this calculation. So the way that we want to think about this is, we know already that 7 atoms of silicon are filling the site. And so we only have a certain amount of space left available. So that's how we're going to want to fill this with aluminum. So the basic formula that we're going to use is, it's going to be, what we want is the total amount of cations that are allowable in that site, which is 8, minus the ones that are already being used up, which is in the silicon column. Now, if we had additional, if, for example, this was a more complex analysis and we, for example, measured phosphorus, which would go into this site, maybe we have a beryllium number or a boron number, both of those are small elements, they would also go into the site. We would have to add all of those things up because those are elements that have to be in the tetrahedral site. Aluminum has the ability to flip between 2 sites. It's large enough to go between the tetrahedral site and the 6-coordinated metal site, but very small phosphorus, very small boron would have to be in the tetrahedral site. And so we would have a more complex equation where it would actually be 8 minus all of the things added together that would have to be in that site. But this is the kind of initial formula. Okay, so you see that now it gives us the right answer, but there's something that we want to be careful about here. Okay, again, in this simplified problem, or I should say in the simplified analysis, it's going to work out. Okay, it's all fine and dandy, but in real life, it could be more complicated than that. Let's say, for example, if we look at this glaucophane down here, we see that we have 8 silicons. That are nominally in the site. And we know that the tetrahedral site can only hold 8 cations. Well, what happens if our analysis is a little off, and instead of calculating out 8 silicons, we calculate 8.03, okay? So if we do the same calculation here that we just did, 8 minus 8.03, you'll see that we actually get a negative number for aluminum. Well, that's unacceptable. I mean, we can't have a negative number for a normalized amount of atoms. And again, that negative number, it's not really real. It's just sort of a reflection of the analytical error, the analytical uncertainty in our analysis. And so what we need to do is we need to incorporate a couple of if statements in here in order to ensure that any of these sort of small analytical errors don't translate into nonsensical numbers like negative numbers or numbers that represent an amount of material that's actually more than what we started with. And so what we're going to do here is we're going to make an if statement out of this, and we're going to say if. You can see, if you're not familiar with how if statements work in Excel, this is going to be a great little lesson for you to take a look at because we're actually going to do a nested if statement. We're going to have 2 ifs in here, and so you'll see what the syntax is for making these statements. So you can see here, if 8 minus, that's the amount that's possible in the site, minus the amount that already has to be in the site, if this number is less than 0, well, what do we want to go into this aluminum cell? Well, if it's less than 0, we obviously don't want a negative number. And so all we can say is, well, if it's going to be less than 0, let's just arbitrarily make it 0. And so we do, if it's less than 0, then we do comma, then we want the value to be 0. And you can see that actually below the formula there, it actually shows how this formula should be written. It goes if logical test, the value if it's true, and then comma, the value if it's false. Okay, so there's the logical test. 8 minus AL8 is less than 0. That's the logical test. Comma, that's the value if it's true. Okay, then comma, and now we want the value if it's false. Well, if it's false, what we're going to do here is we're going to do one additional test. Okay, and so I'm going to actually add another if statement in here. And we have to put another parenthesis in here. And now we're going to add that same thing up again, or we're going to rewrite that same part as before, 8 minus AL8. So it's the same thing as before. But now, instead of testing whether it's less than 0, we're going to test to make sure that that number isn't bigger than the amount of aluminum we actually have available to use, because we don't want to put a value of aluminum into that cell that's more than the amount of aluminum we have available. I mean, let's say that we did this analysis and it actually there was no aluminum in this amphibole. Again, if we had some analytical uncertainty here, there could be a possibility that we would get a number for aluminum when there wasn't even any aluminum measured. And clearly that is also an unacceptable outcome of this. And so that's why we need this sort of nested if statement. And so in this case, we're going to say, if 8 minus AL8, that's the amount that's potentially possible to go into that site, is greater than the amount of available aluminum, and the amount of available aluminum is the normalization factor, okay, times the amount of aluminum that we have available. So that's the total. So this little set right here, $AC8 times R8, that represents the total amount of aluminum that we could possibly have available. So if the leftover space is greater than the amount of aluminum we have available, well, what is the maximum amount of aluminum that we could put into that site? Well, the maximum amount just is the maximum amount of aluminum. So if this is greater than that, then this just has to be $AC8 times R8, right? Essentially, if it's greater than this, then all it can be is that same value. Now, ideally, we hope that it's not less than 0, and we hope that it's not greater than the amount of aluminum. And so the best possible outcome would simply be that it would be the value in the middle, which is what we wanted originally, which would be the 8 minus AL8. That's the amount of space available. Okay, so we have two nested if statements, and so we need one closing parenthesis to close the inner one. Now we need a second parenthesis to close the outer one, and we should be good to go. And I'll hit return, and you can see it didn't change the number here, but now what we've done is we've built in these two safety valves to prevent this number here from being either less than 0 or greater than the amount of aluminum that's present. Okay, so we now have this this kind of setup here. So it's very simple now to calculate this final cell, which will just be these two added together. Sum of the tetrahedral sites, you can see it equals 8, and again, this is consistent with what an amphibole ought to be. Okay, so I'm going to skip ahead now and do the oxygen, fluorine, and OH in that site in order for us to come back and calculate the charge balance. Okay, so I noticed when I was looking at this sheet a moment ago that I actually forgot to add those columns. You can see that I did the tetrahedral site, I did the 6 coordinated site, I did the 8 coordinated site, I did the alkali site, and then I actually forgot the OH site, and so we're going to add those right now. So I'm going to add, let me see here, insert, and I'm going to insert, I think, 4 cells. So we'll do 2, 3, 4. And I will just copy this in order to get the formatting correct. You see? Oh, I actually probably wanted an additional cell, so I'll add one more. Okay. insert another one, and we'll copy that again. And again, I'm changing this is not the correct column heading. I'm just changing these in order to get them set up. So what we want here is we want the OH in the X site, okay, and then we want the fluorine in the X site. Okay, and now I guess normally I would do chlorine, but I guess we're not doing chlorine. No, what we want is we want the oxygen in here. I forgot about that. That's going to be kind of important when we get to the cursitite. Okay, so we want oxygen in the X site, and then finally we want the sum of the X site. Okay. And I will copy the formatting on here so it gets nice and bold. Okay. Let's see if we can get this looking good here. Okay, so we should be good to go. So let's set up this last set of formulas here. So the easiest one is going to be fluorine because, again, there's only one place for fluorine to go in an amphibole formula. It's going to go into the OH site here, and so we can very simply just go, this equals the normalization factor, if I can find the cell here, right there, and then we will multiply it by the number of moles of fluorine, and in this case it's 0. Oh. Almost messed up there. Got to get the time sign in the right place. Click the mole right there. And so you can see there are 0 moles of fluorine present in this. Okay, so the next one we're going to do is a little bit complicated. We're going to calculate the amount of oxygen in the cell. Now, normally when you think of amphiboles, you don't think of any oxygen in here at all. But in fact, in amphiboles like cursitite and in some of these, what they traditionally called in the old days oxy hornblends, these sort of oxidized hornblends that are in extrusive igneous rocks primarily, we see that titanium in a certain site and iron 3 in a certain site actually cause the dehydrogenation of the amphibole, and so we see some oxygen. And the end member condition would be that if we had entirely one atom per formula unit of titanium in the site, that would translate to 2 hydrogens being removed, because essentially we would normally like to have a 2+ cation in here, because titanium is 2 charges above that. We would essentially have to take 2 charges away from the oxygen, so that away from the OH, which would mean removing 2 hydrogens. And so the formula here for oxygen is going to be, this is going to be equal to 2 times the normalized titanium content. So somewhere over here is the normalized titanium, and that will be the normalized titanium. So at the moment we have nothing in there, and so this also will be 0. Okay? And now finally we have one last calculation in this set to do. We want to calculate how much water is present. Well, again, the microprobe can't measure water, so we have to do this by difference. So the way that we will do this is that normally we would assume that this entire site, whether it's full of OH, whether it's full of fluorine, whether it's full of oxygen, or some combination of these, has to be equal to 2. And so what we want here is we want 2 minus, and then we want the sum of these 2 added together. Oh, I think I forgot the, undo what I did here. I must have forgotten to put the equal sign in there. That's okay. I forgot the equal sign here. There we go. And then we want this and this. Okay. And so you see that we indeed get our two OHs, and now we can add the sum of things that are going on in the X site. And it adds up to 2. Okay, so this is sort of the preview of the site fillings. We have our X site filled. And again, we have some unusual formulas here. We have fluorine as sort of our expected formula. We have oxygen as a bit of an unusual formula. And this is, again, based on the crystal chemistry of titanium-bearing amphiboles. So this is something that you would learn about if you read, for example, the Hawthorne et al. 2012 paper on the nomenclature of amphiboles. And then finally, we have this additional calculation for OH, which is just what's left over in the site. Now, technically here, there are rare cases where we have very fluorine-rich amphiboles that we might possibly get a value over 2. And so when we calculate the difference for OH, we would get a negative number here also. So normally we would probably want to put an if statement to protect us from negative numbers here. But I think in this case, I'm not going to bother doing that. It's somewhat unusual getting amphiboles that have so much fluorine in them that they actually overload the X site. But keep in mind that if you are indeed doing a normalization like this and you do have these very fluorine-rich amphiboles, that be wary of this accidentally being a negative number. And if you see that happening, then do put in the if statement to keep this number at 0 rather than as a negative number. Okay, so we have those. We have the tetrahedral site, and so what I'm going to do now is we are going to temporarily skip the rest of these. We'll come back to them in a moment, and we are going to take care of the charge balance, because this will ultimately allow us to calculate the amount of iron 3+ that we have and the amount of iron 2+, which will then allow us to fill those in here in the various 6-coordinated and 8-coordinated M sites. Now, in this first set of test amphiboles, I don't have any iron, but you'll see that I've got iron showing up here in our test fairy gedrite, and there will be a bunch of iron in our mystery amphibole that we will have to figure out not only what site is it in, or what sites it's distributed between, but also what the relative valences are between iron 2 and iron 3. So with that, let me pause the video here, and then we will pick up with doing the charge balance calculation.